Hello everyone, welcome back. In this video, we're going to talk about a method called implicit differentiation. And this method is used when we want to find the derivatives of implicit functions. So let's first start with a few definitions. So the functions that we have dealt so far are called explicit functions, since the dependent variable is defined explicitly by the independent variable. So for example, we have y equals the root of x squared plus 1, or y is equal to e to the x times the sine of x, or more generally, we have y is equal to f of x. So y is solely in terms of the independent variable x. Now sometimes functions can be defined implicitly by a relation between x and y. For example, we have x squared plus y squared equals 1, or the tangent of y is equal to x times y. And so these are examples of implicit functions, as the equation defines y as several functions of x. Now in some cases, we can solve the equations for y as an explicit function or multiple functions of x. So for example, the equation x squared plus y squared equals 1 is the unit circle. And for this case, we can solve for y. So if we were to isolate for y, we have y squared is equal to 1 minus x squared, and then taking the root on both sides, remembering that we have plus or minus, we have that y is equal to plus or minus the square root of 1 minus x squared. So what we have are two functions. So we can call f of x as the root of 1 minus x squared, and g of x is the negative of the root of 1 minus x squared. And so the unit circle can be described by two explicit functions, and these explicit functions correspond to either the upper or lower semicircle of the unit circle. Now for this case, we're able to solve for the derivatives of these functions by using the methods that we learned earlier. However, it is not always the case where we can solve for y explicitly as a function of x. So for example, the equation the tangent of y is equal to x times y, there's really no way of isolating for y in this equation. But fortunately, we don't need to find an equation for y solely in terms of x in order to calculate the derivative of y. And so the method that we will learn is called implicit differentiation. And this will consist of differentiating both sides of the equation with respect to x, and then solving the resulting equation for dy over dx, or the derivative of y with respect to x. Now when we are using implicit differentiation to solve for the derivative of y, it is best practice to use Leibniz notation rather than the prime notation to represent the derivative of y, so that we avoid any confusion between the powers of y and also the derivative of y with the prime notation. So y to the power of 1 may look very close to the derivative y prime. So it's better to use Leibniz notation if we want to represent the derivative of y.
So let's have a look at some examples of finding the derivatives of implicit functions. So here we have the unit circle. So x squared plus y squared is equal to 1. So now let's find the derivative dy over dx. So since we're dealing with an implicit function, we need to use implicit differentiation. So the first step is we differentiate both sides with respect to x. And so what we have is the derivative of x squared plus y squared is equal to the derivative of 1. Now, using the properties of the derivative, we can differentiate each term separately. So we have the derivative of x squared with respect to x plus the derivative of y squared with respect to x, and this equals the derivative of 1 with respect to x. So now let's calculate each term separately. The derivative of x squared with respect to x, we know that by using the power rule, this will be equal to 2x. But now let's deal with the second term to the aside. So we're looking for the derivative of y squared with respect to x. Now what we need to keep in mind is that y is some function of x. And so if we want to find the derivative of y squared with respect to x, what we have to keep in mind is the chain rule. So we can write the chain rule with Leibniz notation. So this will be equal to the derivative of y squared with respect to y, and then we multiply this by the derivative of y with respect to x. And so this is the chain rule with Leibniz notation. So now let's look at finding the derivative. So the derivative of y squared with respect to y, so now we treat y as our variable, and so its derivative is equal to 2y. And this is multiplied by dy over dx. And so the second term is 2y times dy over dx. And then on the right-hand side, we have the derivative of 1 with respect to x, and we know that this is equal to 0. So now we have the equation 2x plus 2y times dy over dx is equal to 0. And so what we're looking for is dy over dx. So we can solve for the derivative in this equation. And so we can move the 2x to the right-hand side. We have 2y times dy over dx is equal to negative 2x. And then dividing by 2y, we have dy over dx is equal to negative 2x over 2y. And if we cancel the factors of 2, our derivative is negative x divided by y. So notice that our derivative is in terms of both x and y, and this will typically occur if our function is an implicit function. And so our derivative will have both the x and y variables. Now in part B, we want to find the equation of the tangent to the circle x squared plus y squared equals 1 at the point root 2 over 2, comma, root 2 over 2. And so to find the equation of the tangent line, what we need are two things. We need the slope of the tangent line, as well as any point which lies on the line. So we're given that the point is root 2 over 2, comma root 2 over 2, and this is on the circle. And all that we need is the slope of the tangent line. So to find the slope of the tangent line, we will look at evaluating the derivative at the point root 2 over 2, comma root 2 over 2. And so the notation that we can use to write the slope of the tangent line in Leibniz notation is where we evaluate dy over dx at the point root 2 over 2, comma root 2 over 2. So the vertical line means evaluation, and we're evaluating the derivative at the point root 2 over 2, comma root 2 over 2. So the derivative from part A was negative x divided by y. And so we substitute the x and the y coordinate into the derivative. So the x coordinate is root 2 over 2. So we have negative root 2 over 2 divided by y, which is also root 2 over 2. We can simplify. So these are both the same values. And so the slope of the tangent line is equal to negative 1. And so now we can write the equation of the tangent line. We have y minus root 2 over 2 is equal to negative 1 times x minus root 2 over 2. So here is the unit circle and the coordinate root 2 over 2, comma root 2 over 2. And this is the equation of the tangent line. So we see that the equation touches the curve at only this point. So for part C, we want to find all points on the circle where the slope of the tangent line is equal to 1. So now we're given the slope of the tangent line, and what we need is the points on the circle where the tangent line is equal to 1. So we know that the derivative from part A was equal to negative x over y. And so what we need to find are all the points such that the derivative will be equal to positive 1. So we will set this to be equal to the slope of our tangent line, which is positive 1. And so what we end up with is negative x over y is equal to positive 1. And if we multiply both sides by y, we have that negative x is equal to y. And so we have one equation involving both x and y. So y must be equal to negative x. So what we need is another equation so that we can solve for the points on the circle. Now, these points must lie on the circle, so it has to satisfy the equation x squared plus y squared is equal to 1. So here we have our system of equations. So we can solve for one of these variables by substitution. So here we are already solved for y in terms of x. So we know that y is equal to negative x. We can then substitute this into the equation of the circle and solve for the coordinates. So if we substitute y into the equation, we have x squared plus negative x all squared is equal to 1. Now simplifying, we have x squared plus negative x squared, which is negative x times negative x. The negatives will cancel and simplify to an x squared, and that's equal to 1. So we have 2x squared is equal to 1. Dividing by 2, we have x squared is 1/2. And if we take the square root of both sides, remembering plus or minus, we have plus or minus the root of 1/2. And if you want, you can rationalize this. We have the square root of 1 over root 2. So if we rationalize the denominator by multiplying both numerator and denominator by root 2, this is plus or minus root 2 over 2. So these are the x coordinates. We can then find the y coordinates. We know that y is equal to negative x. So if one of the coordinates is the root of 2 over 2, then its y coordinate is going to be negative root 2 over 2, which says that our coordinate is root 2 over 2, comma, negative root 2 over 2. And our second x coordinate is the negative of root 2 over 2. And its y coordinate will be the negative of negative root 2 over 2, which is positive root 2 over 2. And so this tells us that our other point is going to be negative root 2 over 2, comma, positive root 2 over 2. And so these are the points on the circle where the tangent line is equal to 1. So here are the 2 points that we found. We have negative root 2 over 2, comma, root 2 over 2. So we see that the slope of the tangent line is equal to 1. And the other coordinate we have is root 2 over 2, comma, negative root 2 over 2. And again, this tangent line has a slope which is equal to 1. Now in part D, let's look for the second derivative of the unit circle. So we're looking for d squared y over dx squared, which is the derivative of dy over dx. So we know that from part A, the derivative of y with respect to x was equal to negative x divided by y. So if we want to find the derivative of negative x over y, we need to apply the quotient rule. So we'll call f as our negative x and y is our g. So using the quotient rule, we have the derivative of negative x, which is negative 1, times y minus f, which is negative x, times the derivative of y with respect to x. So the derivative of y with respect to x is dy over dx. And this is all divided by y squared. So now let's simplify. We have negative y plus x times dy over dx all over y squared. And notice that we have a dy over dx in our second derivative, and we know that this is equal to negative x over y. So we can substitute that for dy over dx. We have negative y plus x times negative x over y all over y squared. So now simplifying, we have negative y minus x squared over y divided by y squared. So now let's make a common denominator in the numerator. So we'll multiply the first term by y over y, which will get negative y squared over y minus x squared over y all over y squared. And now let's write it as a single fraction rather than two fractions. So we'll multiply by the reciprocal of the denominator. So now we can combine the two fractions as negative y squared minus x squared all over y. And then we multiply this by 1 over y squared. And now in the numerator, we can factor out a negative from both terms. And we're left with x squared plus y squared all over y cubed. So we also know that x squared plus y squared is equal to 1. So then our derivative can be simplified to negative 1 over y cubed. So now let's have a look at a few more examples of finding the derivatives using implicit differentiation. So we have the equation 2x squared plus xy is equal to 1. So let's differentiate both sides with respect to x. We have the derivative of x squared of 2x squared plus the derivative of x plus the derivative of x times y is equal to the derivative of 1. So the derivative of 2x squared is 4x. The derivative of x is 1. Now the derivative of x times y. So here we have a product, so we need to use the product rule. So we'll let f be equal to x, and y will be equal to g. So using the product rule, we have 1 times y plus x times the derivative of y with respect to x, which is dy over dx. And that is equal to 0. So now let's isolate for dy over dx. So we'll move all of the terms to the right-hand side, except for the x times dy over dx term. So we have x times dy over dx is equal to negative 4x minus 1 minus y, and then dividing both sides by x, we have negative 4x minus 1 minus y all over x. In the next example, we have the sine of xy is equal to the cos of x plus y. So we use implicit differentiation. We have the derivative of sine xy is equal to the derivative of cosine x plus y. So here we need to apply the chain rule. So the outer function is going to be sine. The inner function is going to be x times y. So using the chain rule, we're going to differentiate the outer function, which is cosine. We leave the inner function unchanged, which is x times y, and then we multiply this by the derivative of the inner function. Now, to differentiate x times y, we need to use the product rule. So x is going to be f, y is going to be g. So using the product rule, we have 1 times y plus x times dy over dx. And this will be equal to the derivative of the right-hand side. And again, we use the chain rule to differentiate this function. So the derivative of cos is negative sine. We leave the inner function unchanged, which is x plus y, and then we multiply by the derivative of the inner function. So the derivative of x with respect to x is 1, plus the derivative of y with respect to x, which is dy over dx. So now let's simplify. We have the cosine of xy times y plus x times dy over dx is equal to the negative sine of x plus y times 1 plus dy over dx. So notice that the derivative dy over dx appears in two different places, and so we need to isolate them to one side of the equation. So let's first distribute all the terms on both sides of the equation. So what we have is y times the cos of xy plus x cos of xy times dy over dx is equal to negative sine of x plus y minus the sine of x plus y times dy over dx. So now let us move this negative sine x plus y dy over dx to the left-hand side of the equation, and the y cos x y to the right-hand side. And so we have x cos of xy times dy over dx plus sine of x plus y dy over dx is equal to negative sine of x plus y minus y times the cos of xy. So now that we have the dy over dx terms on one side of the equation, we can now factor them from both terms. So we have dy over dx If we factor out dy over dx, we are left with x times the cos of xy plus the sine of x plus y is equal to negative sine of x plus y minus y cos of xy. And now the last step is to divide both sides by the square brackets. So dy over dx is negative sine of x plus y minus y times the cos of xy all over x times the cos of xy plus the sine of x plus y. So now in the third example, let's use implicit differentiation to find the equation of the tangent line to the curve at the given point. So we have y times the sine of 2x is equal to x times the cosine of 2y, and the coordinate is pi over 2 and pi over 4. So here we'll use implicit differentiation. So the derivative of y times the sine of 2x is equal to the derivative of x times the cosine of 2y. And to differentiate these functions, we need to apply the product rules. So we'll call y as our f, and sine of 2x is our g. And on the right-hand side, we have another product rule. So x will be f, cos of 2y will be g. So the derivative of y with respect to x is dy over dx. This is multiplied by g, which is the sine of 2x, plus y times the derivative of g. And here we need to use the chain rule. So the derivative of sine is cos. We leave the 2x unchanged, and then we multiply by the derivative of 2x, which is 2. And this will be equal to the right-hand side, which we use another product rule. So the derivative of x is 1 times g, which is 2 times cos of 2y. And then we add this to x times the derivative of cos of 2y. So here we use the chain rule. Derivative of cos is negative sine. We leave the 2y unchanged. And then we multiply by the derivative of 2y. So here we differentiate with respect to x. So the derivative of 2y is 2 times dy over dx. So now let's simplify. We have dy over dx times the sine of 2x plus 2y cos 2x, and this will be equal to cos of 2y minus x. We'll make that minus 2x sine of 2y times dy over dx. So now we'll move the dy over dx terms to one side. So let's move this to the left-hand side, and this will move to the right-hand side. So we have dy over dx times the sine of 2x plus 2x times the sine of 2y times dy over dx. and this will be equal to the cos of 2y minus 2y cos of 2x. So now on the left-hand side, we can factor out dy over dx. So dy over dx, and we're left with the sine of 2x plus 2x sine of 2y. And this is equal to cos of 2y minus 2y cos of 2x. And the last step is to divide by the square brackets. So dy over dx is the cos of 2y minus 2y cos of 2x all over the sine of 2x plus 2x sine of 2y. So that is our derivative. So now we can use this derivative to find the slope of the tangent line. We're looking for the tangent line at the point pi over 2 comma pi over 4. So to find the slope of the tangent line, we will evaluate the derivative at this coordinate. So pi over 2 comma pi over 4. So we substitute x and y into the derivative. We have the cosine of 2 times pi over 4 minus 2 times pi over 4 times the cosine of 2 times pi over 2 all over the sine of 2 times pi over 2 plus 2 times pi over 2 times the sine of 2 times pi over 4. So now simplifying, we have cosine of pi over 2 minus pi over 2 times cos of pi all over the sine of pi plus pi times the sine of pi over 2. So we use the unit circle. We know that the cosine of pi over 2 is 0. Cosine of pi is negative 1. So negative pi over 2 times negative 1. The sine of pi is 0. And the sine of pi over 2 is 1. So simplifying, we have pi over 2 divided by pi. So pi over 2 times 1 over pi will simplify to 1/2. And so the slope of our tangent line is 1/2. So now we can write the equation. We have y minus pi over 4 is 1/2 times x minus pi over 2. And in the next example, we have x squared minus x times y minus y squared is equal to 1. And we want the equation of the tangent line at the point 2 comma 1. So we differentiate both sides with respect to x. So we have the derivative of x squared, which is 2x, minus derivative of x times y. We use the product rule. So this is 1 times y plus x times dy over dx minus derivative of y squared with respect to x this is 2y times dy over dx, and this is equal to 0. So let's simplify. We have 2x minus y minus x times dy over dx is equal to we have minus 2y times dy over dx is equal to 0. So now let's move the dy over dx terms to one side. So we'll move them to the right-hand side. We have 2x minus y is equal to x times dy over dx plus 2y times dy over dx. So now we can factor out dy over dx on the right-hand side, and we are left with x plus 2y. And lastly, we can divide by x plus 2y. So the derivative is 2x minus y over x plus 2y. So now we can use this to find the slope of the tangent line. So we will evaluate the derivative at the point 2, 1. So this gives us 2 times 2 minus 1 over 2 plus 2 times 1. And this will simplify to 3 over 4. And so the equation of the tangent line is y minus 1 is equal to 3 over 4 times x minus 2.